Practice exam 10 of chapter 2 in the book Problem Solving with Differential and Integral Calculus. The formula for the area of a square is d squared over 2, where d is the length of the diagonal. So here we have a Pratt truss design used for bridges and roofs. It consists of squares with diagonals. Part A is what is dA as a function of dd. Let's focus on that. So to get the derivative of a, we change d, the diagonal, by dd, an infinitesimal amount. We calculate the change in a, which we call dA. So I change d by dd, and a changes by dA. I can square that out using the FOIL method, and I get that. I subtract the original area from both sides, which is d squared over 2. Get rid of the a and the d squared over 2. And here we have an infinitesimal squared and an infinitesimal, and we're adding them so we can ignore the square of the infinitesimal. And we can drop the 2's, and we just get d dd. That's dA. So the change in area is the diagonal times the amount that the diagonal changes, as long as it's infinitesimal. So on to part B. Using your answer to part A, provide a good estimate for the change in the area of a square that contains a diagonal strut when the length of the strut is decreased by 1%. So we decrease the length of a strut by 1% of a diagonal strut, and we want to know how the area of the square changes. There's our differential for A. dA is d dd. So all we have to do is substitute in minus 0.01 d. That's a 1% drop. So it's minus d over 100. That's the change. And we're going to substitute in for dd. We really shouldn't do that. We know it's only an estimate. We know that. So we have this. There's d and dd. And we get minus 0.01 d squared. We'd like to have dA in terms of a. So the original area is d squared over 2. So d squared is 2a. And we substitute that in for d. We have, for dA, we have 0.01 minus 0.01 d squared. So we substitute that in, and we get minus 0.02 a. So when the diagonal length drops by 1%, the area drops by 2%. Roughly. We know it's not exact because it's infinitesimal. Let's check it. Easy to check. So we'll start with a square that has a diagonal of 10 meters. Let's pick this one right here. It's got a diagonal of 10 meters and an area of 50 square meters, right? D squared over 2. All right, so we can use the normal equation, plug in the diagonal, and get the area. So if the length of the diagonal decreases by 1%, its new length is 9.9 meters. It goes from 10 to 9.9. That's a 1% drop. And if we can calculate the area for the normal equation, we get 49.005 meters. And if the area drops from 50 to 49, that's 2%. So 50 to 49 is 2%. And that's almost 2%. A little bit higher than 2%. But we left off the d squared term, remember? We assumed it was infinitesimal. If we're going to plug in numbers, we know we're not going to get the right answer. But we can put it back in. We can put the d squared term back in. So this is the exact equation. This is the difference equation. And if you plug in this, dA is minus 0.995. So 50 square meters minus 0.995 square meters is exactly 49.005 square meters. So if you leave out the d squared term, it's going to be a little bit off. And if you put it back in, it's going to be exact. That's differential calculus.